Okay, so welcome to the course today, the second part on the sparse extended information filter. And before we dive into the sparsification and the approximate computation of the mean, just make a brief wrap up to tell you where we are, where we've been in the SEIF. So the key motivation for the sparse extended information filter was obtained when looking into the information matrix that is obtained when doing this filtering. So what you see here on the left hand side was the Gaussian estimate about the robot's pose and the position of the landmarks in the environment, and the corresponding normalized covariance matrix, so normalized to values up to 1. And you can see that this ends up to be a dense matrix with this checkerboard pattern. But the key insight or the motivation for the SEIF was when looking here into this information matrix part, and you can actually see that this information matrix is basically sparse, or has only very few values which are kind of significant. However, in theory, what's not depicted here on the slide is that it has a lot of all these off-diagonal elements are close to 0, but they are not exactly 0. And kind of the key idea of the sparse extended information filter is to do some manipulations here on this information matrix so that it becomes not exactly sparse, but becomes sparse. And so we end up with a very similar estimate, but having a sparse matrix allows us to do some of the computations more effectively. So, and one of the key insights in the sparse extended information filter was to maintain only the links between the robot and a small subset of the poses, of the landmarks, sorry. So you have the robot's pose and a few nearby landmarks, typically landmarks the robot observes plus some more, so it's typically a constant number one uses here. And one only does the kind of expensive operations on this small subset of so-called active features. And whenever the robot moves on, some of the features become passive and some new features become active. And the key step for the sparsification, so for eliminating some of those links between the robot's pose and other landmarks, let's say the robot was before here and then moved over here, so this may have been an active landmark before, now they're becoming passive. The question is, how do we get rid of these direct links between those features that become passive and the robot's pose? And this is a so-called sparsification step, and that's the point where we want to start with today. So we had that SEIF algorithm for SEIF-SLAM, and what we did, the motion update, which was a little bit more complex, involved a couple of transformations exploiting the fact that the information matrix is sparse. And then we had the measurement update, which was rather easy, but very similar to the Kalman filter, except the two lines how to compute the information vector and information matrix change, but the rest was very, very similar. And so the two things we are missing and which we are going to discuss now is the sparsification step, which is the next one. That is, we have that matrix, we have features that were active and should now become passive, and how to deal with these direct links, so these entries in the information matrix between the robot's pose and those features that are supposed to become passive. And that's what we're looking into. So, as this small illustration in the beginning, so if this is, so let's say we have two active features here in the robot's pose, so we have this 3x3 block here in the information matrix, which is typically dense, and then the robot so due to the movement of the robot, we have here elements which are typically non-zero, and then so this entry here corresponds to this link, and if the feature M1 is now the feature that should become passive, I need to actually get rid of this link over here. If I want to eliminate this link over here, it means that these two values here in this matrix should become 0, so there's no direct link between them. This direct link, if you eliminate this direct link in the information matrix, this means that these values become conditionally independent of each other, given all the rest. This is kind of an important property. So if these elements become 0, that means kind of this direct link here is missing. That doesn't mean that these variables are not correlated with each other. It only means they are independent of each other, given I know the rest. But if I don't know the rest, so if I if I invert this information matrix to obtain the covariance matrix, there may be elements in the off-diagonal elements. It only means there's no direct link, that means they're conditionally independent given all the rest of this matrix. Okay, and this is what the sparsification step does. It ignores conditional independence, or it assumes a conditional independence, so and says kind of, given I know all the rest, I assume that these two variables are independent from each other. Although this is not the case in reality. Therefore, sparsification is an approximation. So what the sparsification step does, it kind of removes these elements over here. So this link here is gone, removes the link between the feature M1 and the pose of the robot. And so we need to update this covariance matrix here accordingly. So this means that xt plus 1 and m1 become conditionally independent given the rest of the variables. So in this case, for example, m2. Also in theory m3, but this currently hasn't contributed to this matrix, so we leave that out. Okay, and the effect of the sparsification here, you can see some of the kind of information is moved to these other links, because if we remove one of those links, you can actually approximate that by manipulating these two links as well to be closer to the real estimate, not just setting those elements to 0. So what sparsification means is, as I said, ignoring links which exist, so assuming conditional independence. And in the case of the sparse extended information filter, this is done between the robot's pose and those features or landmarks that have been active and now turn into passive ones. This is kind of the key thing in sparsification. It's kind of the overall picture clear what we aim to do.
This part we active become passive. What does exactly mean? We are more certain about that, or
no? So moving from an active landmark to passive one has nothing to do with how certain we are about the estimate. It just means that we are considering a constant set of active landmarks for which we want to maintain the direct links or dependencies between the robot and those features. So we just take for example, 4 or 10 features. We just say kind of the expensive updates we only do based on the robot's pose in these whatever 4 or 10 landmarks. However, if we move through the environment, we should actually change the landmarks which is directly linked to the robot's pose. And these are typically the landmarks in the vicinity of the robot that are observed by the robot. So I need to kind of move my number of active features, and if I add a new one, I have to remove an old one.
It's a FIFO.
Sorry?
It's a FIFO list. We just enter one landmark and just...
Yeah, so let's say we assume we could do it in different ways, but standard ways to say we have, let's say, 10 active landmarks. Because the bigger you make this set of active landmarks, the more costly your operations get. Clearly. Because if you put the number of active landmarks to the size of the matrix, nothing would have been 1. Right?
Are the active landmarks just the observable landmarks?
Not necessarily. So typically you have more in there. Typically you set it to a constant number.
It's constant.
Sorry?
Is that a constant number of landmarks?
Typically it is constant, but you typically have all the ones you observe in there, plus potentially more.
Okay.
I mean, there's no real need actually to make it constant. You could only also adapt it while operation based on the computation time you have. So that should be possible, yes. But typically you set it, so the typical implementation uses a constant number, but in theory there's no real reason why you shouldn't be able to adjust this number on the fly. Okay, any further questions about the thing in general? Okay, so let's have a look into sparsification in general. What does sparsification mean? So the key idea is we want to replace a distribution here about 3 random variables. So this is unrelated to the SLAM problem in general. Say called an A, B, C by different probability distribution which should be close to P. Let's call it P tilde. And in a way that, for example, in this case, A and B are conditionally independent given C. So given we know C, the other variables are conditionally independent. That means in this approximation, P P of A given BC should be equal to P of A given C. Right? So we simply generate a new probability distribution. We say we take the old one, the original one, but we assume that we can replace every occurrence of P of A given BC by P of A given C. So given we know C, we say A and B are conditionally equal. That's clearly an approximation, which is not true in general, but this is kind of the approximation error we use, the difference between those two distributions. It is an approximation, so we kind of lose information in here. But we do that, this approximation, in order to obtain a sparse information matrix, which makes the rest of our life easier. Okay, so then we can actually write that. It's we are P of A, B, and C is P of A given BC times P of B given C times P of C. So this is standard factorization. There's no approximation at the moment. And then the approximation comes to the game where I say P of A given BC is P of A given C. So this is the approximation I do. Those two terms stay the same. So then what I can then do, I can simply add a P of C divided by P of C, so this is 1, assuming that P of C is bigger than 1. And then I can group these two terms over here and these two terms and say this is P of A given P of A and C times P of B given C divided by P of C. And this is exactly my approximation. So I approximate this distribution by this distribution, which can be expressed exactly in this way. This is what sparsification does. So the sparsification makes an assumption about, or assumes a conditional independence, which is definitely not necessarily true, but this is where the approximation error of the sparsification is there. And if I do that, so as I said, if I assume a conditional independence, that means that some of those elements of this information matrix get 0. Okay? Most of you seem to have a question about that. Okay, so the only thing I do an assumption. Assume a conditional independence. Say these elements are the same, that's what I assume. And if this is not the case, I do an error in this step, but I hope this error is small. That's what sparsification does. Okay. So the goal in the sparsification of the sparse extended information filter for SLAM was to compute an approximation of the information matrix so that it is and stays sparse. So in every point in time, I want to have, so after conducting a sparsification step and then doing my manipulations, I want to have a sparse information matrix. And sparsity means in the here that we have only a kind of constant number of off-diagonal non-zero elements in this information matrix. So I don't care how large my matrix is, I have just a finite number of non-zero off-diagonal elements. So there should be only a small number of variables which are directly connected with each other, which have a link between each other. So the number of links a variable has with others should be limited. So, and most of those links I actually generate in the motion update step of the SEIF, because then in this small matrix which contains robot's pose and all the active features, I actually typically obtain a dense matrix. So I say I have my dense matrix, that's okay, that this is dense, because it's just a constant number, a small set. But if I move on through the environment, I need to add in new features to this active set, so I should remove old ones. And this removal of the old ones should result in the fact that I eliminate the direct links between the robot's pose and those landmarks that become passive, so that when the robot moves on, these landmarks are now passive and don't require any further update because there's no direct link with the robot's pose. Because the problem was, when the robot moves, all these given that it has the connection to all these active landmarks, in the update step, this kind of block matrix got dense. And this is the thing we want to avoid, because if we would continue that, we have simply links in this information matrix between all features and the robot's pose with kind of a densely connected graph, if you see it as a graph. So all variables are dependent on each other, have a direct link. This is what I wanted to avoid. So what the sparsification step does here, it maintains only the links between the robot and a few landmarks, and these are the active landmarks. All the others are eliminated by the sparsification step. So whenever a landmark is active and becomes passive, I kind of remove those links. The passive one stays passive, nothing is added to them. So I only need to take care of those who are currently active and should now become passive. And this also leads in the end to also limits the number of connections the landmarks have among each other, because the only reason why a landmark is connected with other landmarks is because they've at some point in time been joined in the same set of active landmarks. So this is kind of a local property. So landmarks, all landmarks have connections to a few other landmarks in this passive set, but not to the robot's pose. Because they must have, in order to generate a direct link between two features, it means that they had to be together in the active set. Since the active set is small and bounded, this is also bounded. So the key thing is limit the updates to the active landmarks, especially when the robot moves. So that's a set of active features and passive features, which are here shown on gray. And so you can see that all these features are connected kind of with their neighbors. So if you look to this one, these are the group which they are directly connected. But it's not, this one is not connected with, for example, this feature or that feature over here. So we have 2 or 3 types of landmarks: the passive ones, the active ones, and in the special case of the sparsification, the active ones which become passive. Because these are the ones that we want to eliminate the links. So we can write m, the number of landmarks we have, into m plus, which are the active ones. M0 are the so far active ones that should, after the sparsification step, be passive, and m minus, which are the passive ones. Okay, any questions about that? That's kind of clear. Okay, what we now want to do, we want to remove the links between M0 and XT. Okay, so remove the links between the robot's pose and those landmarks which have been active but should become passive. And this, as I said before, the sparsification is equal to assuming a conditional independence. So given all the other landmarks, my assumption is that the robot's pose and the feature that become passive are dependent. This is the assumption I do. The important thing is here is no change in the links of the passive landmarks. So I don't touch the passive ones and I don't touch those ones. So I touch, the sparsification step touches those which are currently active and stay active, because some of the information of those which become passive is transformed to the other links. That's what we had before. The important thing is the passive ones are not updated at all. So this part of the information matrix doesn't change. So the change is only local. And this is one of the reasons why, again, we can do that in constant time, because we do all operations very locally in our matrix. And I've said it quite a few times, it's important to know, sparsification is an approximation. So what I want to do is we have our probability distribution about the pose and all the landmarks, conditioned on the observation of the controls. And we can write that as the pose and the 3 landmarks, because these 3 groups of landmarks assemble all landmarks. And now we have to do some approximation. This is the approximation which is done with sparsification. Okay, so we start with what was exactly written here on the last slide. P of x time. So the only thing I dropped here is the dependency on given the observation and the controls. Because otherwise the slide is pretty populated with these and u's which don't contribute really. So assume there's everywhere written a given g and u. So the first operation I do in here is just a factorization, an exact factorization. by saying that, so I can factorize the robot's pose given all the landmarks times all the landmarks. Now I said in the SEIF formulation, I said, because I have my active landmarks, the estimate about the robot's pose, so the passive landmarks do not contribute to the estimate of the robot's pose, given I have my set of active landmarks. Of course, the update step in the SEIF only depends on the active features. So I can simply set them to 0. So we ignore them. So I say, just set them to a value 0 because their values don't contribute to xt. Okay. So what's the SEIF? Your SEIF.the update based on the active. Okay. So the 0 is given the active landmarks. The passive landmarks do not matter for computing the robot's pose, so set them to 0. One step. The next thing I do is that I say, this is the sparsification step from here to here, where I say, given all the other landmarks, m0, and here the m minus, I do this approximation, this potential error, by assuming that the robot's pose is independent of the features that become passive. This is what I introduced by this sparsification step. This is done in here. So I replace this line, this operation, by this operation. So we're eliminating this m0, because this is what the sparsification does. It assumes this conditional independence. If it's true or not, it's nothing. So it's actually not true in general, but that's the approximation error the sparsification does. Once I have that, I can actually just rewrite that as this product. So the only thing I did, I kind of move the m plus the active landmarks in here and then divide it by the probability of the active landmarks given what was conditioned. So just a rewriting step. And this is now my, that should be a dot, comma here. So this is my approximated probability distribution. This is what the sparsification does. So sparsification results in eliminating the direct links between xt and m0. And this is the assumption that they are conditionally independent given all other landmarks. That's the reason why in this case here we set m minus to 0, that not removed it completely from the distribution, because the sparsification assumption says given all other landmarks. So we need to maintain those landmarks, although they don't contribute, actually values don't contribute to the estimation of xt given the assumption we have in this. Okay, so this is exactly the term we had before, just now we added these z and uts, so we have this term over here. So this is the thing we need to compute now. So we need to replace the information matrix and the information vector by a new information matrix, a new information vector that is computed according to this quantity. This is the update. So we manipulate our information matrix and our information vector so that according to this equation over here. And this is then the sparsified belief, sparsified Gaussian in canonical form. Is there a question about that?
The links between the two landmarks, how we just get more certain about these two landmarks when we omit the passive landmarks, but we just roughly...
This comes automatically from this operation summary. So there's nothing we kind of manually tweak in there. This comes automatically by these operations in here. So the only thing we did is here, we said, we assume at one point in time in our belief between the xt and the m0 conditional independence given the rest, there's everything else follows from these steps.
Here we should keep m0, not m minus, because m minus is the passive one.
Yeah. But this is not, the important thing is we eliminated m0 because we said that the robot's pose is independent from m0 given all other landmarks. This is the assumption we make. So we eliminate m0 from the belief. So when I compute xt, get rid of the n0 because we assume them to be conditionally independent. All the others are just operations we did by saying applying a factorization or the definition of conditional independence over here to get this fraction. This sparsification is only this removal of this n0. Okay, so the important thing here is, or not the important thing is, but the thing what we need to do is now, these are all Gaussian beliefs. So this can be expressed by computing the information matrix, the approximation by a sum of 3 information matrices, one corresponding to this term, minus one corresponding to this term, plus one corresponding to this term. So you can say, you can express this as a sum of 3 matrices. And what mainly happens when computing these individual terms, so I don't want to go into the exact details how these guys are computed, but what in the end happens is we apply the rules for marginalization and for computing conditional probabilities of the Gaussian distribution. That's the thing we do. And we apply matrix inversion lemma for a few terms. So if we, for example, just as a reminder, so in the Gaussian case, in the moment form, the marginalization was easy because I just can cut out something from the covariance matrix. For the information matrix, or for the canonical form with the information matrix, the conditioning is the easy tool. So if you have the distribution, let's say you have P of A given B, you want to express from a belief you have about P of A and B. And let's say your information matrix can be written as A, B, A, B. Then this means that the covariance matrix of this belief, A given B, is just this term over here. A. So this is the conditioning, which is easy, but now the marginalization is more involved in both the inversion, and for the Gaussian in the moment form it's exactly the other way around. It's kind of the rules for the conditioning and the marginalization of the Gaussian distribution. I also put on the slide, it was on the website, it was requested a few informations about background material also on the Gaussian, and there's also kind of the marginalization and the conditioning rules on a single page just depicted. So if you want to read it there, the material is on the website. And this I can just use to compute the 3 matrices and then some other matrices. It requires quite some manual matrix manipulation since here. Again, said I'm not sure if this adds a lot of value for understanding what's going on, therefore kind of I dropped that. But so you need to compute those individual terms which correspond to these probability distribution, which in the end, what they basically do, they take the big information matrix, they cut out parts of that, the projection, invert parts of that, and reassemble them. Because this is in the end what happens if you do this conditioning and marginalization with the Gaussian here. Okay, so now we have computed this omega tilde, so the approximation of the information matrix, which is now kind of the sparsified version of it. We also need to update the information vector. This can be done quite easily because the approximate information vector can be expressed as the approximate information matrix times the mean estimate, and this one can be expressed by the original information matrix minus the original information matrix plus the approximated one. So then I can say this is the original information matrix plus the difference between the approximated one and the original one times the mean. And now this I can replace to the original information vector, therefore I kind of did this manipulation because this quantity I already had. And so what I in the end need to do, I take my old information vector I had before the sparsification and just take the difference between the information matrix and the before and after the sparsification times mean. So this is an update. So this guy I have from the previous step. There's a difference between the information matrix that was introduced due to the sparsification and this. Okay, So given that I have that, I can define the complete sparsification algorithm. What you see in here is this big ugly block. This is exactly the sum of these three matrices. These FM matrices, as I said before, these are just projection matrices which take the high-dimensional space and project it here to the active landmark that become passive, to the robot's pose, and exactly this set. And so you have these projections from the big matrix into smaller blocks. Manipulate that in a way. I don't want to derive all the things in here, but they can be derived by this, by taking the three information matrices which correspond to these individual distributions, and then just add them up. As I said, from this derivation, I'm not sure how much this helps the understanding of this sparse extended information filter. Therefore, I removed that here. But yeah, so I think it was a better choice than now for 15 minutes deriving these terms. That's the sparsification step. So after the sparsification step, we get a new information vector and a new information matrix, so that for an updated belief, so that the information matrix is sparse. Are there any questions about that sparsification step? The key idea is that we assume conditional independence between the robot's pose and the landmarks which become passive. That means we eliminate or remove the links from the information matrix between the landmarks that become passive and the robot's pose. Just this algorithm tells you how to do that. This is an approximation, because in theory, all these variables should have all direct links between each other, because if you know something about one variable, it tells you a little bit about another one. But the direct link is typically very, very small. This is why this whole huge information matrix had a lot of elements which are close to zero. And this is the approximation we do in order to maintain that sparsity. Okay. So again, we have the 4 steps of the sparse extended information filter, and we have the only thing which is missing is the update of the mean. As I said before, the problem is the mean was needed for a couple of operations, so we needed it in the motion update step to apply the motion function, the motion equations, because we needed to know where the robot is, at least the first 3 dimensions of the mean, x, y, theta. For the measurement update, we needed also some parts of the state space, basically the robot's pose, and the position of the landmark that the robot is observing, because I need to compute the expected information, and therefore I need to know where the landmarks are. And also for the sparsification step, I needed the mean in some dimensions. These are those which are changed, especially both elements between the active feature, the currently active features, and the active feature which becomes passive. All the landmarks involved in that. For them, I need the mean. For the rest, the information matrix doesn't change, so therefore I need it for this update here. So I kind of need the mean estimate for the robot's pose, for the active features, and the active ones which become passive. So m plus, m0, and xt. For those, I need the mean estimate for these computations here. The problem was when I compute the mean by the inverse of the information matrix times the information vector, which would be the exact thing to do. This is a costly operation. All the benefits, so for everything was constant time operation, which is very, very efficient. It's super greatly efficient. Would vanish because this requires a matrix inversion of the whole matrix. Okay, so as I said, we needed the mean for the motion update, measurement update, and the sparsification step. And so if I said I already did an approximation in the sparsification step, so let's not compute this term here exactly, let's also introduce an approximation. So let's compute an approximation, especially since we only need a small part of the mean vector and not the whole mean vector. So we don't care about all the passive features in here. We only need it for small stuff. We can actually say, let's treat that as an optimization problem and simply say, we want to have an estimate of the mean, which simply is the maximum of the probability distribution. Given that it's a Gaussian over here, the maximum value of the Gaussian is at the mean. Optimized. If I kind of do a whatever gradient descent or whatever technique I use in the end, in this probability distribution, for maximizing it, I will end up at the mean. So if I do this optimization, I'll actually find the mean. Since I do this only for a small subset of the variables, I have the hope that I can do that kind of in an efficient way. Don't need to compute all the dimensions, just for a small subset. So how do you find the mean that maximizes this probability density function? How do you find the maximum of a function?
Take a derivative.
Compute the first derivative. Set it to 0. So after setting it to 0, what do we need to do then? Solve a system of linear equations, and then we typically iterate that process. Simplification. That is one way to approximate that mean. You can do other things, like you can do a gradient descent. You can have different ways for doing this, for solving this optimization problem. But that's kind of the standard thing you basically should know from school, how to find the maximum function. And that's the thing you can do here. And the key trick is you simply do something similar to that for a few iterations, for a constant number of iterations. Because you say, I have small dimensions, I do that in every step, I should never be too far away. So just execute a constant number of iterations. And this is kind of important to do a constant number of iterations to not lose our constant time updates. Therefore, the result I get here is quite likely not to be the exact mean, but it's an approximation of the mean. And since the system says I already do an approximation in the sparsification step, I simply do a second approximation here first. So, I don't want to go into the details how this is done here exactly. While we process in that course, we will look into these optimization problems in more detail, because this is one alternative way to address the SLAM problem. Treat simply everything as an optimization problem. And so we'll go into the details here, and once we have done, that should be easy to understand what happens here. But at the moment, I would like to leave it here. We just execute these 4 steps or a similar procedure in that, and then come up with the mean. Yes, please.
I'm not understanding why do you have to iterate?
Because this will be only correct in one step if you have, there would be a linear, yeah, okay. So this whole, so if you want to find the minimum of that function, you have nonlinear functions involved here, so you need to have this linearization step. So you need to exclude the linear. Because in the end what you do is solve a system of linear equations. So there's linear equations in there, and therefore you need to iterate the process. It only will be a one-shot go if the function you're minimizing has a certain property, or can be expressed as a linear or quadratic arrow function, then one shot will be sufficient. But this is not the case here to iterate. But as I said, this kind of all the things we will do around Christmas, or closely after Christmas, for several hours you're doing this optimization stuff, and then I think you will better understand what's going on. Okay, so what we did, we completed all the important steps of the sparse extended information filter. And all 4 steps are done, so we do all these updates and then return the new information vector, the new information matrix, and the new mean. So how does this look like if we would do the exact operation and if we would do the sparsification? So what you see here on top is if the set of active landmarks would be simply the whole state space. So no sparsification is carried out. So you see there was the closest link to every landmark. You see all those landmarks are densely connected with links. This is how the covariance matrix looks like, and this is how the information matrix looks like. This is what the SEIF does in this case for 6 active landmarks. So you see the black links between. This is the current active set of 6 landmarks that everyone is using, and you can see here again the network of links between the landmarks is much smaller than here. Here it's completely dense, and here it's kind of, you can at least visually see that this is less dense than the one on top. And so you only have links between those landmarks which have been in the same active set. This is the covariance, normalized covariance matrix you get out of that, and the information matrix. Then the information matrix, it's very hard to see any difference at all. For the covariance matrix, you see a little bit, so some of the parts are a little bit lighter, but you can still see kind of these block patterns you can recognize in here or here. You still recognize in here as well. So here the overall structure is roughly maintained. Okay, so the key advantages of this SEIF is that it is a roughly or approximately constant time complexity. I say roughly because you have the approximation of the mean, which is simply abort at some point in time. And the other reason, what I haven't talked about here, is finding the correspondency. So which landmark I see is which landmark in the map. And this is an operation which may not necessarily be conducted at constant time. And that's kind of, therefore I said roughly constant time. So if you have the known correspondencies, you abort your iteration and fixed limit, you end up with a constant time algorithm. And this is compared to quadratic time of the EKF. So this is a huge, huge win. So it's irrelevant how big your map is. If you have a constant number of CPU cycles, you can always do your operations. And this is really nice for a robot. It doesn't matter how long it navigates through the environment, it can always do all its computations, for example, on board, because the computations don't get more difficult if the size of the map increases. This is kind of an important or very, very nice property. I mean, still, the system has a linear memory complexity because you need to store all the landmarks. So at some point in time, the system may run out of memory if the memory is simply smaller than the number of landmarks which are out there in the environment. That's maybe a limitation. Again, this is compared to the quadratic complexity of the EKF, where we have to maintain the full dense covariance matrix. It's again a big win. Only linear memory complexity compared to a quadratic complexity of the EKF. However, SEIF-SLAM is less accurate than EKF-SLAM because we did approximations. So we have the approximation of the mean and we have the sparsification step in here. So the accuracy should be worse than for the EKF. We actually look how the things relate in terms of CPU usage and accuracy. So what you see here, so this is the EKF with these small rectangles over here. This is the SEIF algorithm. What you see here is a number of landmarks and the CPU time which is needed. You can see here if kind of this ends up to be a quadratic increase over here. And this thing is, listen, given a certain number of landmarks you have, it turns out to be a constant. I mean, there may be some effects in there if you just count the time the CPU needs for, let's say, swapping operations. You have to reload memories from the cache or outside the cache. So there may be some variations in here, but all in all, it's roughly constant. This should be constant over here, while this one grows quadratically. So you can see, if you have more than 200 features, it's worse to go for the SEIF than for the EKF. And also, if you look to the memory usage, we again have the quadratic complexity here, and it's just a linear increase because you just need to maintain the sparse information matrix and the information vector, and both grow linearly with the number of landmarks which are added. And if we, however, compare the error which is done, so the average error of the landmark, so this is here now the EKF, and this again is the SEIF. Over here you can see the SEIF has a bigger error, so bigger error estimates. Bigger error estimates. There's bigger errors in its estimates compared to the EKF. The EKF is a better estimator. If you don't care about complexity, if you have enough computational resources to solve your problem, go for the EKF, don't go for the SEIF. But as the size of the map or the environment increases, you will pretty quickly experience limits of the EKF, and that's just with the side axis performance. You can also see how the number of active features, so this was the question, is this a constant or not? So we can set it to a constant. We can see that the bigger we make that number, the bigger the value gets. So this is not necessarily linear increase, but it's just monotonically increasing. So if you have 4 landmarks, we need a certain number of update time. And as we increase the number of active features, the computation time goes up, and this also makes sense because the more active landmarks we have, the bigger the block of our information matrix, which gets denser, and those operations get more costly over here. But more relevant is probably how does the error behave of the EKF and the SEIF, depending on the number of active landmarks. So So if I have a small number of active landmarks, which you can show here, so I really have a pretty big error. And as I increase the active features, the error goes down. So let's say if you go for around 10 active landmarks, it's the difference between the SEIF and the extended common filter gets smaller and smaller and smaller. Even at least in this example, for around 10 active landmarks, you should perform quite well. Or the result is not too far away from the EKF. So this is an error on the mean estimate. One note is that the estimates of the uncertainty estimates the SEIF typically produces are overly confident. So you're too confident about your estimate. This can be problematic, for example, for things like data association. So be aware that the estimates of the uncertainty that the SEIF produces tend to be overly confident. There are alternatives for doing this, so there have been extensions proposed to the SEIF by Justice, work on insights and sparsification in SEIF, and they can show when you manipulate, you change the sparsification a little bit, sparsification rule, you actually perform much better and you're really close to the exact EKF estimate. But the problem is then these operations don't constant time anymore. So there have been extensions to that, but if you want to get better, you typically use the time capabilities of the SEIF. So in summary, the sparse extended information filters are an approximation of the extended information filter, and therefore also for the extended common filter, because the extended information filter was just the dual representation of the extended common filter in canonical form. What it does, it neglects links between the robot's pose and some of those landmarks, the active ones which turn to passive ones, by the sparsification, and it computes the mean estimate or recovers the mean using an approximation. So these are the two approximations the SEIF does. However, these approximations allow for constant time operations if we have known correspondences, what we assumed here. So if you observe a landmark, we know to which landmark this corresponds to the in our map. Let's say if you have a very good feature descriptor, you may assume that you can quite well identify the feature. If this is not the case, you have to change things here. It is a linear time memory complexity compared, which is an advantage to the EKF, but it has an inferior quality than the EKF and also the extended information filter. Because, at least without approximation, that should perform exactly the same way that the EKF, maybe except some numerical issues. Okay, so again, some literature. The sparse extended information filter for SLAM, you find the chapters 12.1 to 12.7 in the Progressive Robotics book, and also most of the derivations I've shown here are in the book. And also if you're keen on computing the approximation for the information matrix in a more exact way, the math of the derivations are in that book. It's something which I jumped in. Okay, so are there questions at the moment for the sparse extended information? Yes, please.
Yeah, one question about like the application.
Mm-hmm.
Could you say, okay, I want to create a map,
Mm-hmm.
and say, okay, maybe with the AKF I would have more EKF, I would have more exact estimates,
Mm-hmm.
but with this sparse I can just use more landmarks and actually get a better map? Because I have more landmarks.
So that's, the question is, what do you define as a better map? The thing is, if you define the better map as the displacement between the features in the map and where they are in reality, adding more features shouldn't really help you here.
Yeah.
Because in the end, if you even think of the EKF, they are all kind of correlated. So if you move one feature a little bit in one direction, all the others move as well. So if you may see from that point in time that you from this point that you say, I just have a certain number of CPU cycles, for example, on my robot which I can execute, and I'm in front of the design decision: should I take the SEIF or should I take an EKF? You say if I have an EKF and I may be able, let's say, I can be able to use 10 landmarks only. If I use the SEIF, I can take the 10,000. Then for building a map of the environment and localizing yourself in that map so that you can do navigation, the SEIF may be the better choice because you simply have much more landmarks you can use to localize yourself. In this respect, the map may be better for the navigation task if you compare the features you have to the estimates where they are in reality. Maybe, or this question, it really depends on the current setup. But for the navigation task, you say just any CPU cycles available, what should I do? In this case, the SEIF is very likely to be a better choice. Yes, please.
We observe 3 landmarks in the observation. Do we replace all those 3 landmarks with the 3 other we have observed previously, and those 3 become passive, or we choose?
If you set the number of active landmarks to 3, that would happen.
I mean, is there any possibility to miss any landmarks because they are close to each other and we observe them at the same time, and we do one by one passive and active? We don't do at the one time 3 landmarks become active and 3 other become passive.
I mean, it depends a bit how you execute your SEIF. So if you say you have n landmarks, you want to maintain as active ones. You just get one single observation at a time. You will make, as soon as your active set is bigger than n, it's n plus 1, you have to throw 1 out. That's what the algorithm tells you. Typically, how it's implemented is that you take all the observations at once, take them, and then in the update step, iterate over them. But in the end, you need to define your active set. If you say it's 10, you have 10 landmarks in there, you get 10 new ones in, you have to throw the 10 old ones out. There's nothing you can do about that, unless you vary that number. But typically, this set is constant. Any further questions on the side? Okay, so then let's make a 5-minute break, and then I will give a short wrap up on the Kalman filter and all its friends, and then we continue with the particle filter as an alternative estimation technique, which has some advantages of the Kalman filter. So for now, we kind of leave this intensive matrix manipulation aside. It won't appear in the next chapters because we don't work with productive forms, and so I hope it's easier to understand what's going on for the next set of filters, and they can actually be grasped quite well without needing to dive that detail into the matrix manipulation. So this may be appreciated by some of you. Okay, thank you.